Dr. Rico here. This is a lecture from my course, System Dynamics. The syllabus link is in the description. Okay, welcome to the Laplace transform chapter, lecture def. The Laplace transform and its inverse. First, the Laplace transform. The two-sided definition of the Laplace transform was encountered in the preceding lecture. This is rarely used in engineering analysis, which prefers the following one-sided transform. Let f be a map from the positive reals to the reals, be a function of time for which the function of time is equal to 0 for time less than 0. The Laplace transform L, a map from the space T to the space S of f, is defined as the Laplace transform of f of s equals this integral, which looks very similar to the Fourier transform integral, right? Of particular note in terms of difference are this bottom limit, which is 0 instead of negative infinity, and this factor in the exponential, which is s instead of j omega, okay? The Laplace s, the complex frequency introduced in the preceding lecture. As with the Fourier transform image, it is customary to capitalize the Laplace transform image. For example, f of s, capital F of s, is equal to the Laplace transform of f of s. Now, let's slow down for just a moment and reconsider what spaces the Laplace transform was mapping from and to. It's mapping from the space of real functions of time to the space of complex functions in the S-plane, okay? So T and S, you can get more complicated with how you define those spaces, as we do in this footnote. But at the end of the day, they're two function spaces, okay? So the Laplace transform actually maps one function to another function. A bit of an unusual beast for us, and it's important to recognize that there's some terminology issues here, and we'll review a few of them in a moment. As with the two-sided Laplace transform, if the transform exists, it will do so for some region of convergence, ROC, a subset of the S-plane. It is best practice to report a Laplace transform image paired with its region of convergence. On the imaginary axis, meaning in the S-plane that sigma is equal to 0 and s is just equal to j omega, and the Laplace transform is the Laplace transform of f of s is equal to this, which is the one-sided Fourier transform. Looks just like our regular Fourier transform, but this bottom limit goes just from 0 to infinity instead of negative infinity to infinity. Causes endless problems, but it turns out that the Laplace transform is almost always taken to be one-sided, and the Fourier transform is almost always taken to be two-sided, so we have a sort of ball of wax that we have to deal with when we try to go back and forth. Therefore, when the Laplace transform exists for a region of convergence that includes the imaginary axis, the one-sided Fourier transform also exists, and the one-sided Fourier transform of f of omega is equal to the Laplace transform of f of s, where s is evaluated at j omega, or haphazardly using f to denote both transforms, f of omega, the one-sided Fourier transform, is equal to the Laplace transform, where s is evaluated at j omega. Now let's talk about terminology. The terminology in the literature for the Laplace transform and its inverse introduced next is inconsistent. The Laplace transform is at once taken to be a function that maps a function of t to a function of s and a particular result of that mapping, technically the image of the map, which is a complex function of s. Even we will say things like the value of the Laplace transform f of s at s equals 2 plus j4, by which we really mean the image of the complex function f of s evaluated at s equals 2 plus j4. That was the image of the Laplace transform map of the real function of time f of t. You can see why we shorten it. The inverse Laplace transform. As with the Fourier transform, the Laplace transform has an inverse. Definition of the inverse Laplace transform. Let S be a complex number, the Laplace S, the complex frequency, and f of s, a Laplace transform image of a real function f of t. The inverse Laplace transform, denoted L to the minus 1, is a map from S to T, S being the space of complex functions on the S-plane, T being the space of real functions of time. This inverse Laplace transform is defined as this integral, okay? 1 over j2 pi, integral of f of s e to the st ds. We evaluate that integral from sigma minus j infinity to sigma plus j infinity. As illustrated in this figure, def.1, it can be shown that the inverse Laplace transform image of the Laplace transform image of f of t is equal to f of t, and vice versa. In other words, if you take the inverse Laplace transform of the Laplace transform of f, you just get f back. If you take the Laplace transform of the inverse Laplace transform of f, you just get f back. That is, the inverse transform is a true inverse. Therefore, we call the Laplace transform and its inverse a pair, or a transform pair. Let's take a closer look at this figure, okay? This figure has t, the space of real functions of time, time domain functions, and s, the space of complex functions of complex frequency s. Now, these two spaces can be mapped to each other via the Laplace transform going from t to s and the inverse Laplace transform going from s to t. So this, if you're going from left to right, then if you started here, you had f of t, you take the Laplace transform and you get this f of s, then this would be called your pre-image of the Laplace transform, and this would be called the image of the Laplace transform. Conversely, if you started here at f of s and you took the inverse Laplace transform back to f of t, then you would call this your pre-image of the inverse Laplace transform, and this the image of the inverse Laplace transform. So you can go back and forth, and you can continue to go through this loop, and it never changes, right? If something changes, you broke it, okay? Something happened. It's not good. All right, so that's the inverse Laplace transform. Okay, so there's a detailed view of the first figure that we looked at, given in the second figure, which is actually def.2 in your notes. So let's take a look at it. We have, again, the Laplace transform going to the right, the inverse Laplace transform going to the left. But here we've expanded out. We aren't looking at the space of functions that map real functions of time and the space of functions that map complex functions of s. instead, we look at one function of time, f, little f, from the non-negative reals, time, to the reals. Okay, so this is what the Laplace transform inverse maps to, and the Laplace transform maps from, over to the S domain, or here is one function, big F, in the complex domain. We take the S-plane, S being an element of the C plus set. We use plus because the only possible way that we can get convergence here is if sigma is positive. So we typically just look at the right half plane of the S-plane for the domain of F, and we map to a complex number, which is the codomain of big F. So we see here that the Laplace transform is actually mapping functions to functions, and the inverse transform is doing the same thing, but just the other way. Okay, so back to the example now, returning to the troublesome unit step function, f of t being equal to the unit step function. Calculate its Laplace transform image, f of s. Directly applying the definition, we see that f of s is equal to the integral from 0 to infinity of f of t e to the negative st dt. Now we're going to substitute in for f the unit step function of time. So we have the integral from 0 to infinity of f of t, which now we're going to put in the unit step function. However, in this interval from 0 to infinity, the unit step function is always having the value 1 times e to the negative st dt, which, taking the antiderivative, we get this expression, and evaluated at the limits from t equals 0 to infinity. Now, an interesting thing happens. When we evaluate something at infinity, truly we are evaluating the limit as that variable goes to infinity. So we take the limit as time approaches infinity with this term, which is just this, but we've expanded out s to be sigma plus j omega t. We have the other term that comes from evaluating this antiderivative at time equals 0, which is nice and easy. E to the 0 is 1, so we have a negative 1 over s, and a negative here, so this is going to produce a 1 over s. So if this term with the limit goes to 0, then this emerges as the Laplace transform, 1 over s. Now, when does this go to 0? This is going to go to 0 as time goes to infinity, as long as this term has a real part here that's negative. The imaginary part essentially gives us an oscillation, right? That's a sinusoid that happens. So we're going to get a sinusoid, and as long as it is a damped sinusoid, as long as that sinusoid has an envelope function, which this real part provides, the real part of the exponential provides, that draws it to 0 as time goes to infinity, this limit will be 0. And otherwise it doesn't have a limit because it will continue to oscillate for all time. Okay, even if sigma is 0, it will oscillate for all of time. Okay, and there will be no limit. The limit won't exist. Okay, this exclusion of sigma equals 0 is important here. So if sigma is 0, we have an oscillation, so it never converges as we go off to infinity in time. And therefore there is no Fourier transform. So we're doing the Laplace transform, which allows us to essentially scoot over just a little bit with our convergence into the right half plane, whereas the Fourier transform is stuck on that j omega axis. And being stuck on the j omega axis in this case yields an integral that does not converge. So we've seen how to take the Laplace transform now, and it yields 1 over s. Our region of convergence is for the right half plane, exclusive of the imaginary axis. Both the Laplace transform and especially its inverse are typically calculated with the help of software and tables, such as the table in the appendix, lap.1, which includes specific images and important properties. We will first consider these properties in lecture lap.pr, which is upcoming, then turn to the use of software and tables in the lecture lap.inv, where we focus on the more challenging inverse calculation. See you then.